E-flesh, a robotic skin with magnetic tactile sensing. In a world where robotics continues to evolve at an unprecedented pace, the development of advanced materials that emulate the complexities of human biology remains a crucial frontier. One emerging innovation, known as e-flesh, represents a significant step toward creating robotic skins that not only protect and insulate but also provide sensory feedback that closely mimics human tactile perception. By integrating magnetic tactile sensing into a flexible, compliant material, e-flesh is poised to transform applications spanning from humanoid robotics and prosthetic devices to complex human-machine interfaces. Robotic skin, often termed electronic skin or e-skin, was initially conceptualized as a way for robots to develop a sense of touch comparable to that of human skin. Traditional robotic systems rely on rigid sensors or simple pressure switches at strategic points, resulting in a limited and jerky performance when interacting with complex environments. This limitation spurred researchers to look for solutions that could not only detect force but also mimic the nuanced, distributed sensory feedback seen in natural skin. E-flesh represents the latest evolution of this research. By incorporating flexible electronic circuits, soft polymers, and, most intriguingly, magnetic tactile sensing elements, e-flesh offers superior adaptability. The magnetic components are embedded in a pliable matrix, enabling sensors that can not only respond to direct pressure but also to nearby magnetic field variations. This dual capability enhances the resolution with which robots can interpret their surroundings, leading to significantly improved functionality in tasks that require delicate manipulation or subtle force feedback. The magnetic tactile component of e-flesh is both innovative and integral to its design. Traditional tactile sensors often rely on piezoresistive, capacitive, or optical methods to measure pressure changes. However, these approaches can be sensitive to environmental conditions and may require cumbersome calibration routines. In contrast, magnetic tactile sensing leverages the interplay between magnetic fields and magnetoresponsive materials. Within e-flesh, tiny magnetic particles or thin films are dispersed among an elastomeric substrate. When pressure is applied or the skin is deformed, the spatial relationships between these magnetic inclusions change. These alterations modify the local magnetic field distribution, which is then detected by integrated magnetoresistive or Hall effect sensors. Because these sensors are less susceptible to interference from factors such as temperature fluctuation or electromagnetic noise, the result is a more reliable and consistent reading of tactile information. Moreover, the inherent flexibility of these magnetic elements ensures that the sensor network can endure repeated bending, stretching, or twisting without losing functionality. The potential applications for e-flesh with magnetic tactile sensing are broad and transformative. In the realm of robotics, nuanced tactile sensations enable more effective human-robot interactions. For instance, humanoid robots equipped with e-flesh can better perceive their environment, detect subtle changes in pressure, and avoid causing harm during physical interactions with people or delicate objects. This improvement not only enhances safety, but also improves the performance of robots in intricate tasks such as surgical assistance or disaster response. Prosthetics stand to benefit immensely from such innovations. A prosthetic limb outfitted with e-flesh could provide users with levels of sensory feedback previously unattainable with traditional prosthetic designs. This would allow for a greater degree of manipulation and a more natural, intuitive control over artificial limbs. The integration of tactile feedback would enable amputees to perform tasks that require a delicate touch, like handling fragile objects, improving their overall quality of life. Moreover, the technology could revolutionize wearable devices and smart textiles. Imagine clothing embedded with e-flesh technology that monitors touch, pressure, and even subtle deformations, providing real-time data for health monitoring or immersive virtual reality environments. As the technology matures, there could even be crossover applications in fields like soft robotics or interactive art installations, where the tactile feedback of surfaces can alter digital experiences dynamically. E-flesh, a cutting-edge development in the world of robotic skin, embodies the future of sensory technology. Through its innovative combination of flexible materials and magnetic tactile sensing, it offers the promise of more sophisticated, reliable, and human-like sensory feedback. As this technology continues to mature, its impact could reach far beyond robotics, influencing prosthetics, smart wearables, and interactive devices in ways that challenge our current understanding of machine perception. Ultimately, eFlesh represents not only an intriguing technical achievement, but also a glimpse into a future where artificial systems might perceive the world with an almost human sensitivity.